is FRQ number 1 from the 2017 AP exam. And I think this is a pretty revolutionary question. This could be on the AB exam or the BC exam. And this is something they did a couple years ago. Actually, it won't be on the AB exam this year because it's a volume question. But anyway, in other years it could be. So they give you a tank height. This is actually very much like the Forrester football problem we did at the start of the year. If you remember, Forrester gave us a table, I think, that had cross-sectional areas of footballs. And we kind of drew the graph, and we actually used that to find the volume by estimating an integral at that time of the year. So they give us a tank. The thing is 10 feet tall, and they give us the area of horizontal cross-sections of the tank. Notice they don't tell you what shape they are. They could be circular, they could be square cross-sections, they could be pentagonal cross-sections, they could be some kind of weird squiggly shape. Literally doesn't matter, okay? They tell you the function is continuous, and it's decreasing. So this tank is getting thinner, basically, as you go up to the top. So I kind of giving you an image here. This is not exactly what's happening. If you look there, it's actually the widest at the bottom, 0 feet off the base. It's got an area of 50.3 square feet, and then it kind of drops. So this isn't exactly like that. But for example, they say that 2 feet off the ground, a cross-sectional area is 14.4 square feet. They say that 5 feet off the ground, a cross-sectional area, and again, it may not be a circle, it could be any kind of shape, but a cross-sectional area is about 6.5 square feet. And then it's getting smaller as it gets up to the top. Again, this actually should get wider all the way to the bottom to completely match the data. I'm just trying to give you a way to visualize what's happening here. So this is really kind of a variation on the square cross-sections problem or the half circle cross-sections or something like that. And if you do this the way Forrester asks you to do these problems, even though Forrester didn't include a lot of problems like this in his book, this concept still works out really nice. Remember, Forrester's concept is to write a DV statement. What's the volume of one of those slices, okay? And again, people always worry about, well, what's the shape? The shape doesn't matter because they already told you the area, okay? So the volume of one of these little slices, okay, these are all going to be prisms or cylinders or something like that. Those slices in the slab method, it's always the area of the base times the height. That's all that's going on there, okay? Well, they're telling us the area of the base, okay? The area of the base is going to be that A of H formula. The height is going to be a little, they're representing the height is H here. Okay, you're putting in a height and you're getting out an area. So that's going to be a DH. So my DV statement here is just my A of H DH. And remember, you just take the integral of these from the lowest point to the upper point. And what that integral is going to do, it's going to find the volume of this little slice. And it's going to find the volume of the little slice that's here. And it's going to find the volume of the slice that's here. And it's just going to add these up all the way to the top. So anyway, these are actually really super simple integrals. We're just taking the integral from 0 to 10, because that's the height of the whole tank, of that A of H function dH. Now, they didn't give us the function in part A. They just asked us to estimate it. So we're really just basically doing a Riemann sum here. And doing it that way. So now the information they give you, this tank starts out with cross-section areas of 50.3, and it kind of drops. So the A of H graph and height would look something kind of like this. So they're asking us to do left Riemann sums with the graph. Anyway, so let's see. The first point there is at 0, 50.3. The next point is at 2. It actually drops to 14.4, so my graph is not very accurate, but that's okay. The next point is at 5. These are left Riemann sums. So next point is at 5, 6.5, and so on. So anyway, the area of this first one is just going to be 2 times 50.3. The area of this one's going to be 3 times 14.4, and so on. And you can just kind of add all of that up. Let's go ahead and take a look at their solution here. You don't need to watch me write all that down, but anyway, so you can see here they have that setup there, And you can see the 2 times the 50 plus 3 and the 3 times 14.4 and so on. There's no initial value or anything. We're starting at the bottom, extending to the top. Do make sure you have the correct units there. It's cubic feet for the volume. All right. Anyway, moving on. Part 2 asks us if this overestimates or underestimates. If you go back and look, they tell you here that A is continuous and decreases, okay? So coming back to my picture over here, for a left Riemann sum, if you're picking values on the left, you're picking the high points on a decreasing function. So you should be able to say that it overestimates because f is a continuously decreasing function and a left Riemann sum was used, okay? Don't say I drew a picture and the rectangle's stuck out above, okay? That may help you remember what the rule is, but to explain it, it's decreasing and it's a left Riemann sum, okay? And see those two things there. We only get a point for that one. All right. Part C asks us, actually gives us a function now. So before we were just using a table and estimating, and now they say, haha, we do have a function. Here it is, okay? We should just be able to dump this back in. This was a calculator question. So you should be able to dump that back into that original integral that we set up. It's just going to be the integral from 0 to 10 of 50.3 over e to the 0.2h plus h dh, okay? Again, it's just the area of the base times the height. Okay, they gave us the formula for the area of the base. We don't have to square anything. We don't have to multiply by pi. We don't even have to know what the cross-sectional shapes are. This function is just going to turn them all out for us. So it doesn't get easier than that. And we'll go look at their answer for that one as well. Again, you can stick this in the calculator. And so, again, from a setup standpoint, they're going to need to see what did you take the integral of. You took the integral of that function f that they gave you. And apparently you get that, and then they do kind of word it out with correct units there. Okay, let's look at the final part of this one. I think it's a related rates problem. It says water is pumped in the tank when the height is 5 feet, the height is increasing, okay? When you're doing a related rates problem, you always want to list out your variables. So the height increasing, that's a dh dt, that's an increase, so it's positive. So that's 0.26 feet per minute. They want the rate at which the volume of the water is changing, so we want dv dt here. Okay, well, if you go back here, we created a volume function in the previous problem. If you come back here, that was a volume function, right? But that's the entire volume. We really want to do a volume from 0 to some set height. Let's see. So it doesn't look like, it looks like we can use whatever variables we want here. I guess we'll go from 0 to h, right? Because we're going from 0 to whatever the actual height is. And then since we're using an h there, we want to use some other variable here. So let's do like 50.3. We'll call this over e to the 0.2x plus x. Dx, maybe something like that. Okay, that's our volume function. So whatever the volume is, you're going from 0 to whatever height. So I guess that would be v of h, basically. And anyway, we want the rate of change. So the derivative of that integral function is just going to end up being the 50.3 over e to the 0.2h plus h. And then remember, you have to multiply by the derivative of the inside function with respect to t, because we're taking the derivative with respect to t. That inside function there is going to be h, so that's times dh dt. And at this point, they tell us that that's 0.026, and they ask us to do this when the height is 5, so you're filling in a 5 there, and you're filling in a 5 there, and that should give us our final volume. Again, you don't need to see me type all this in a calculator. The setup is where most of the points are going to come from. Obviously, sticking the calculator will probably get you an additional point at the end. Let's go see if I'm totally off base here and how they show it, because that's obviously the most important thing. Okay, so yeah, they did almost exactly what it did, 0 to the height, and they changed the variable there. They took the derivative of the integral function. The derivative of the integral function is going to end up giving you f of h times dh dt. And then they substituted everything in there. They didn't show a whole lot of work for it, but that's all that's going on. So kind of a weird problem, but really just does the same things we've been doing. Just, again, a little bit weird because our volume function involved an integral, and I don't think we've seen that mix of things, but we've certainly seen the second fundamental theorem. So anyway, neat problem.